Good day and welcome everyone. My name is Michael Whitaker. I'm the manager of the International Safeguards Group at Oak Ridge National Laboratory, and the talk this session is on safeguarding uranium enrichment, the challenges of large gas centrifuge facilities. And with just a little bit of background, I began my career over 30 years ago, 1981, working at the Oak Ridge Gaseous Diffusion Plant, K25 site here as part of the Manhattan Project, working in the Operations Analysis and Planning Division. So I had the opportunity to be exposed both to uranium enrichment operations and also introduced to International Atomic Energy Agency safeguards, IAEA safeguards, in particular the development of the approach to be used at enrichment facilities. So throughout the 30 years, continued to be involved in uranium enrichment, IAEA safeguards, and non-proliferation. The activities continued to evolve and remains new to this day. So those of you considering a career in non-proliferation, please look forward. Please don't hesitate to call me for any information. So my talk today, a brief overview of uranium enrichment in terms of the facilities and operations that have a relevance in terms of IAEA safeguards, a brief overview as to what the IAEA actually does in terms of safeguarding an enrichment facility, and then jump into the current challenges that are out there and some of the technologies that are being investigated to respond to those challenges. So I understand we'll have a question and answer at the end, but please don't hesitate in the course if there's a burning question to break up the monotony of me speaking. Uranium enrichment dates back a long time. We're approaching the 100th year anniversary of the discovery of isotopes. It took place in 1913. Of course, in regards to uranium, dates back to 1939 when it was learned that neutrons fission and the lead up to the Manhattan Project. But as early as the 1920s and 30s, a variety of the separation processes were being developed to separate extremely small quantities of some of the noble gases, neon, chlorine, and others. And at that time, there was R&D on gaseous diffusion, thermal diffusion, and gas centrifuge. So in some regards, separation technology is a very old technology. It wasn't until the Manhattan Project of World War II that there was a need to separate very large quantities of isotopes on an industrial scale. And we saw the production of enrichment facilities here in Oak Ridge for the purpose of separating the U-235 isotope from the predominantly U-238 material. The gaseous diffusion process was the most economical at the time. There was some work on using the calutrons here at the Y-12 plant, but it was a very energy and costly enterprise, so gaseous diffusion became the technology of choice. We built 3 very large plants here in the United States. The fusion plants were also built in the United Kingdom, in Russia, in France, and China, and proved to be the technology for providing most of the highly enriched uranium for the weapons programs in those countries. It was then in the 60s through the 80s that we saw the peaceful uses of uranium enrichment become a growing factor in the separative capacity market. As the peaceful nuclear fuel cycles were being developed, most of these reactors were relying upon slightly enriched uranium on the order of 3 to 5% enriched to run the pressured water reactors. At that time, the economics became more of a factor. The gas centrifuge separation technology, requiring less energy than the gaseous diffusion, became a technology of more interest, and we saw gas centrifuge programs emerge in the U.S., in Russia, in England, as well as non-nuclear weapon states such as Germany, the Netherlands, Japan, and even in the 70s, work taking place in Australia and a few others were looking at some R&D activities. A brief overview of the fuel cycle. Uranium in the form of U3O8 ore concentrate is mined out of the ground. Typically in the better uranium mines, the amount of uranium ore is on the order of 0.1 to 0.2%. So 1 to 2 out of 1,000 mass units would contain the uranium ore. This material is sent to a mill where the uranium ore material is separated from the rest of the dirt and gravel and other info to concentrate it to a level of 70 to 80% U3O8. This is often referred to the yellow cake as the product. At this time, there's been no change in the isotopic, so it's still natural uranium, which has a U-235 concentration of what, audience? You didn't hear that. The audience gave the right answer of 0.711%, although they did not give it very enthusiastically. So, fortunately, they're not on the camera right now, but we may change this as we go through. So this U3O8 in the form of powder, bulk material is sent to a conversion plant where the material is converted to a UF6 material. Generally, it comes out as a gas in the production. It's put in cylinders where it's in a solid form. This UF6 is still natural in terms of the U-235 concentration. This then becomes the feed to an enrichment facility. The enrichment facility will have two output streams. One is the product with the stream that is enriched in terms of the 235 concentration, and the other will be depleted since we neither create nor destroy U-235 atoms in this process. This enriched UF6 will be sent to a fuel fabrication facility where through a variety of processes it will be converted to a uranium oxide in the pellets, put in the rods, and then assembled into assemblies, which is then sent to the power reactors for the production of electricity. If you look at a gas centrifuge, some of the common elements are common to all machines by the different technology holders. There is a rotating section as shown in the right part of the screen where the major items that we look at are these rotors, which are hollow cylinders. At the top, let me go back, is end caps, and at the bottom is an end cap to keep the UF6. We've got a virus screen here. Let me defer that. That rotates so that the UF6 is introduced into this rotor, which then spins at a very, very high speed. At the bottom is a pivot bearing, allowing it to rotate on a single point. At the top is a suspension bearing, which does a couple of things. It balances the centrifuge so it rotates in the vertical position, and it also provides some lift to take the weight off of the pivot at the bottom. So those are the rotating parts. The schematic on the left shows the other non-rotating parts, in which generally this rotor is placed inside of a casing that provides two functions. One, there we go again. One, it creates an empty space on the outside of the rotor such that you can produce near vacuum conditions to reduce the drag on the rotor to allow you to hit higher speeds. Secondly, this casing provides protection in the event that this rotor crashes. We've got an item spinning at a very high speed. You don't want it going all over your plant floor, so anytime a rotor would crash, it would be contained inside this casing. Inside this casing is a very special feature in that you've got this tube that is inserted inside. This tube has 3 chambers such that the material at 3 different enrichments can be contained. There's my mouse. So the feed will come into one portion of the chamber and then be reintroduced somewhere in the middle of the centrifuge. You'll have a scoop on one end and a scoop on the other end, such that material at different concentrations, both depleted and enriched, can be taken off separately, and then all 3 of these pipes will exit the top of the centrifuge. There are 2 different types of separation effects that take place inside the centrifuge. One is the radial separation, where the U-238, having 3 neutrons more than the U-235, is slightly heavier, such that when you're spinning it at a high degree, the heavier material will tend to be closer to the wall of the centrifuge than the inside. So there is a very slight separation that goes from the inside of the cylinder to the outside. Based on the aerodynamic effects of the scoops and the baffle, you also create this counter-current flow shown by the little green arrows inside that also causes a separation to take effect vertically along the centrifuge as well. So a rough rule of thumb, or if you look at the theory, the amount of separation that can take place inside a single centrifuge is proportional to the length times the velocity, or how fast you spin it, to the 4th power. So those who are building centrifuges are looking to make tall centrifuges that spin at very high speeds, recognizing the physical constraints of being able to balance these machines and preventing them from crashing. So here's 3 different sets of pictures. Again, the exterior, you're only looking at the casing, so you are not able to see the actual materials of construction of the rotors themselves, or the suspension, or other sensitive information about the centrifuges. Those on the right, these are Russian machines. You can see a bank of 4 different centrifuges with many hundreds placed together for a separation test. The top picture is actually one taken from the Dutch plant in Almelo. These are taller machines. I think here in the background is a person standing, so you get a feel that these are on the 10 to 15 feet high type of centrifuges. And you can get a look at the height versus the diameter of these machines. Again, tens of these connected together. At the bottom is a picture that the Iranians put on the website showing machines at Natanz for a rough scale. You can see a chair sitting here on the left. So somewhere in between the two in terms of height, etc. The other thing that is common to enrichment process, not only are the centrifuges, but the way the centrifuges are connecting together. So from a safeguards perspective, we're interested in all this overhead piping that determines which of these machines are connected in series versus which ones are parallel, which helps us know a little bit about the throughput and the capability to use these machines. So in terms of the enrichment cascade, it is the capacity of the individual machines, and then secondly, the configuration, how they're connected together. We use this schematic to give a brief overview of the actual physical operations that take place on an enrichment plant. First of all, this UF6 that is produced where? Well, one of the participants was a little more enthusiastic that time. At the conversion plant, natural UF6 is produced and put in these large standardized cylinders made out of typically steel that may hold 10 to 14 tons of material. These are shipped to the enrichment plant either by truck or by rail or some mechanism. Then the nuclear material accountancy starts to take place, and I think there's other lectures in this course about material control accountability, where cylinders are first weighed so that you've got a value for the gross weight of these cylinders based on the operating plant's requirements. Some number of these cylinders may either be NDA'd or statistically sampled to verify the purity and the isotopic concentration of the material. And then this material is put into a storage queue until it's time for the contents of a feed cylinder to be transferred to the process. At this point, UF6 at ambient conditions is basically a solid. It's a solid white crystalline material with a small amount of gas above it. The triple point where liquid is present is at higher temperatures. So this material is basically a very safe chemical composition for storage on the site. When it becomes time to introduce that material into the cascade, and we use this diamond figure to represent the cascade, the cylinder is placed into some type of a heating chest or an autoclave where heat is applied to increase the rate of transfer of the material. For a slow feed rate, you may just heat it slightly, 100, 150 degrees, where the solid will sublime into a gas at a faster rate to be pulled off the cylinder into the cylinder. Or for very rapid transfers, as we used at our diffusion plant, it may be heated up past the triple point up to the order of 180 degrees Fahrenheit or so, where the solid is melted into a liquid, and then this liquid is very rapidly evaporated into a gas for feed into the plant. So the actual conditions are based on process information. But ultimately, the goal is the same, to transfer the UF6 from this cylinder into the cascade. These cascades run continuously, 24 hours a day, 365 days a year from the day they are started till the day they are shut down. So while this feed is continually produced, you've got both this product and this tail stream simultaneously being withdrawn continuously as well. This material is also collected into separate cylinders. This is done by a variety of techniques, but basically you are cooling the gas down so that it will desublime back from a gas into a solid. For accountability purposes, these cylinders are then weighed on very precise accountability scales. The tails, there are limited commercial products that would use it, so basically these are placed in the long-term storage at the facility. The product cylinders are then homogenized and sampled to make sure that the product material meets the specifications of the customer in the contract, put into a short-term storage area, and then ultimately shipped to the customer, which is, again, typically the fuel fab. So these are the major operations that take place at the plant. Now, this is a very busy schematic showing where a lot of these operations take place. You see cascade halls, feed and withdrawal areas, weighing and sampling areas, storage areas, laboratories, decon and maintenance areas, scrap recovery and waste treatment. It's a busy slide because an enrichment plant is a busy operation. You've got these large cylinders moving on-site, off-site, in the storage areas, into the feed and withdrawal areas, and gas to the cascade. These are the solid lines that you see primarily in this upper corner of the schematic. What you also see by the dashed lines are a lot of the minor flows that take place. These can be samples that are moved from sampling areas or the Cascades or the decon to the analytical facilities for accountability purposes, environmental health and safety purposes, or the others. From a safeguards viewpoint and accountability viewpoint, we are interested in all these flows where material transfers from one container to another container or from one side on the facility to another side on the facility. So we have an interest in all of these activities. So let's look to see what large-scale plants are in operation today. There are two that are still using the gaseous diffusion plant, and let me start at the bottom. Within the United States. Earlier I mentioned we built three. The K-25 plant here in Oak Ridge was shut down in 1985, or at least placed in standby in 85 and ultimately shut down in 87. There was one in Portsmouth, Ohio that was shut down in 1991, I believe was the right date, or right there in the early 90s. So the third, the Paducah plant in Paducah, Kentucky, is still in operation. It came online in 1954, 1955, and has been running continuously for 56 years. They're hoping to keep it running another couple of years anyway as they're switching to centrifuge. The other large one, George Best 1 in Tricastin in France, operated by the Atomic Energy Commission of France, is a large plant. It started in 1982, I believe it was. The French are currently building a large-scale centrifuge plant, and so we're expecting GP1 to shut down sometime towards the end of 2012. There are three plants being operated by a European enrichment company, Urenco, one in Gronau, Germany, one in Almelo, Netherlands, one at Capenhurst in the United Kingdom. These plants started operation in the 80s and 90s and have continued to increase in capacity. All three of these plants now range between 3,000 and 5,000 tonni SWU, or in terms of kilogram SWU, 3 to 5 million kilogram SWU per year in capacity. Japanese had operated a number of demonstration facilities in the 80s and 90s, and now is working on a commercial plant in Rokasho, Mura province in Japan. The capacity had got up to 1 million kilogram SWUs of capacity. They've had some problems, and currently all their cascades are shut down, but they are developing that next generation machine and plan to bring that online. The other major enrichment operator is Russia. They had 4 very large gaseous diffusion plants being built in the 50s and 60s, and then dating back from the 70s through the 80s, they converted their capacity from diffusion to gas centrifuge, such that by the early 90s, all of their separation capacity is based on centrifuge. Reportedly, the capacity of each of these 4 plants range from about 2.5 to 12 million SWU, with a total capacity on the order of 27 million SWUs of capacity. So not a great number of plants, but these are large plants. Switching gears a little bit, let's talk a little bit about the IAEA. I think there's some other lectures in this series that will refer to IAEA practices. Just as a brief review, the IAEA applies safeguards at facilities at the invitation of the facility owner's government. So these are voluntary activities that take place to provide the international community assurances that the operations at these facilities are as declared. The IAEA was created in 1957, so they have now been in existence over 50 years. Over 150 member states are party to the IAEA, and I guess it's important to point out you can be a member to the IAEA without being a signatory to the Non-Proliferation Treaty. There's a lot of overlap there, but that being a member of the NPT is not a requirement for being a member of the IAEA. The IAEA as an organization is actually a very small organization, only on the order of about 2,300 staff members supporting 6 different departments. There are representatives from approximately 100 different countries. As a UN organization, they try to divide the jobs proportionally among the member states. Within the Safeguards Department, who we're primarily interested in, they have about 500, a little over 500 employees. Just a couple of statistics from the year 2010 regarding the activities of these 500 employees, of which there's only about 200 that act as inspectors who go to facility. They're responsible for applying safeguards to over 600 facilities and lofts, that's locations outside of facilities. They apply safeguards to about 172,000 SQs, that's significant quantities of material, and the IAEA definition for highly enriched uranium, that represents 25 kilograms of U-235. For plutonium, that represents what, audience? Oh, much better. 8 kilograms of plutonium. In 2010, they performed a little over 2,000 inspections, and their budget is extremely small, on the order of 120 million euros, which with the current exchange rate is on the order of about $150 million. Very small budget. The objective of IAEA Safeguards and Enrichment Plant is threefold. First of all, they want to be able to provide the timely detection of the diversion of any declared material, uranium material. And here we're looking primarily at UF6. Secondly, they want to be able to detect in a timely fashion the misuse of the facility for 2 different types of scenarios. The first is the production of excess material at the declared enrichment, because as we'll see, if you've got a source of excess LEU, you are well on your way towards being able to produce direct use material. And then thirdly, and probably most importantly for us, is be able to detect the misuse of the facility to produce higher than declared enrichments, in particularly HEU, highly enriched uranium. The IAEA definition of HEU is what, audience? 20% or more in terms of the enrichment of the U-235. Primarily, we're looking at 90+% per se. So if a plant is a commercial plant for producing low-enriched uranium for a regular nuclear fuel cycle, typically that product is on the order of 3 to 5% enriched. So this third objective is to verify it's not 20% or higher being produced at that plant. The IAEA safeguards measures are threefold. The first of which is to look at nuclear material accountancy, that is accounting for all the material on the plant site as declared by the operator. Secondly, they supplement nuclear material accountancy with containment surveillance that helps provide continuity of knowledge in between measurements, such to reduce the amount of remeasurement that the agency has to take place in inspection. And the third is the inspection itself, sending inspectors to the site to make sure the actual conditions on the ground match both the operator's records on the site, and also those records they receive directly from the national authority. So what are the major challenges at an enrichment plant? Four of the more predominant ones that I want to address is, first of all, there's not a current means of independently verifying the actual separative capacity. An enrichment plant is, and here for the rest of this, let me focus primarily on the gas centrifuge technology, were those centrifuge rotors that I showed at the beginning. What did I say? You actually don't see the rotors themselves, you see the casing. By looking at the casing, you cannot tell the materials of construction. You may get some feel for the length of it, but not how fast it's going. And what did I mention? The separative capacity is based on the length times the velocity to the fourth power in terms of theoretical separation capabilities. So, by looking at one of these devices, you will not be able to see what the capacity is. Also, to get the information to do that is sensitive, probably classified information by the technology holder, who is bound not to share information that would allow someone else to produce weapons for to be able to produce material for a weapons program. So as an inspector, they will not be able to get precise information on the height or the speed. So without knowing that, they cannot know the number, the capacity of a machine. And even if they were able to count all the machines, a big part of the separative capacity is actually how it's being utilized. What is the feed rate? What is the actual settings at the time? So there's not a magic device that the inspectors can independently verify what the capacity of these machines or plants are. So that's a significant challenge. As I mentioned earlier, many of the aspects of the design and operation are classified or proprietary. One of the facts that I didn't mention, if you would have added up the capacity of all these plants, you would have seen that the amount of installed capacity in the world is on the order of 50 to 60 million kilogram SWUs of capacity. The current demand on the market is on the order of 40 to 45 million SWUs of capacity. So there's more capacity than demand. So there is a commercial competition going on in terms of contracts. So information about actual operational efficiencies are proprietary information as well. Already mentioned earlier the budget constraints of the agency, a very small budget, a large number of facilities to safeguard, and only a couple hundred inspectors. And then finally, as part of the comprehensive safeguards agreements that the IAEA signed with the national governments, one of the commitments on behalf of the IAEA is not to impact normal operations. Because if you really wanted to know what was going on at one of these sites, you could come in and say, well, let's shut this place down for a month. I'll count everything. I'll measure everything. Then I will really know what material is here and to make sure the records are correct. However, as I mentioned, an enrichment plant runs continually forever, and so shutting down a plant, is a significant impact on operations. Also, when they're shut down, they're not producing material that can be sold. So it is a challenge to be able to verify these declarations without unduly impacting operations. Beyond the scope of this series, we could talk about these HEU production scenarios and scenarios for how a plant could be misused to produce excess low-enriched uranium. But some of the indicators associated with those are shown here. Let me first talk about some of these pictures. This is a picture showing the end of a cascade that shows some of the typical piping that goes out. It's probably too difficult for you to read. I'm not sure if I can read it right here myself. Uh-oh, my cursor has died. I'll see if it'll come back up. Here is one of the feed pipes where the UF6 goes into the Cascade. I think up here is one of the product pipes. There are a lot of other pipes that go in that may contain instrument air, emergency purge, and everything else. And so even if I declare what material is supposed to be in what pipes, there's a lot of other pipes. And if you're looking at the facility misusing their equipment, you have to be able to independently look at all of these activities. The second picture down here, this shows a portable feed and withdrawal cart that can be used during startup or during recovery from an emergency situation like a power failure or something else, which shows the capability to link a small cylinder to the Cascade through a pipe here. So there are operational reasons why facilities are laid out and operated the way they are. However, these have a relevance in terms of safeguards. So the activities that are potential indicators of HEU production are as followed. Reduced throughput. How is a reduced throughput a potential indicator? There's no answer from the audience, so I'll go ahead and give this one. If you are using a portion of your Cascade to produce HEU, by definition, you are not using that equipment to produce LEU, so the total amount of LEU coming out of your plant might be less than the installed capacity. So, you say, okay, well, if the throughput drops, is that a strong indicator or a weak indicator? Well, it's difficult. What did I say? There's already an overcapacity, and so maybe they don't have the contracts. So the fact that they're not producing at full capacity shouldn't by itself be a surprise, and that's not by itself a strong indicator. Secondly, what else did we talk about earlier? We can't just look at it and tell what the capacity is anyway. On the nameplate, they may say, I've got 1 million SWUs of capacity. Maybe they've got 1.2 million SWUs of capacity, because we cannot independently verify that. So it is an indicator. It's a weak indicator. I showed in the picture portable feed and withdrawal equipment. There is a capability. You can feed and withdraw directly from the Cascade, which you might want to do if you want to isolate one number of centrifuges for misuse. It is standardized equipment that has a legitimate function. What you have to do in terms of an inspector or their interest is making sure this equipment is not being used when it's not appropriate to be used. So it's a good indicator, but it's a difficult one to detect. The misuse scenarios will all require the use of extra cylinders, undeclared cylinders, or cylinder-type containers. If you are going to have undeclared material, you have to have something to put this material in. UF6 as a material is beyond the scope of this lecture, but it's a very corrosive, toxic material, so there is some specialized containers needed. You would not carry it around in a bag, or it's not a powder, so you have to use cylinders. However, you don't necessarily have to use these international standardized containers. You could use something like a propane tank that can contain material. It's made out of steel, so it can be used for UF6. So part of the challenge of detecting an undeclared operation is being able to recognize the existence of undeclared containers capable of containing UF6. Earlier I mentioned, in addition to the centrifuges, what is this other aspect that is of safeguard relevance? The piping, how these centrifuges are connected together. Again, without going into great detail, if you wanted to enrich natural uranium up to 3 to 4%, you may have to have what we refer to stages of equipment you may have to have on the order of 15 to 20 stages of equipment to go from natural to LEU. This is based on the specific separation factor associated with a specific centrifuge design. If you wanted to go straight to highly enriched uranium, you may need 50 to 60 of these stages connected in series. So one of the concerns from the safeguards perspective is our machines that would normally be connected in parallel reconfigured to operate in series to produce higher enrichments. To do that, what you may do is be able to route the way the material flows through these machines, which is why we're interested in valve settings. And the next bullet there, actually reconfiguring the piping to be able to feed and withdrawal inside the cascade or change the flow of material through these machines. One of the stronger indicators associated with this direct production of HEU is the radiation signatures coming from the HEU. If you're using non-destructive assay instruments, NDA instruments, one of the things that you're looking at is the intensity of the gamma rays associated with the U-235 isotopes. And here in particularly, we're looking at the 185.7 keV gamma ray from U-235. The higher the enrichment, the more U-235 is present, the stronger that signal is. Also, you would get a increased neutron yield as well, not from the 235, but from 234, which we haven't discussed in this presentation, the reaction between U-234 and the fluorine that's in the gas. Nevertheless, the higher the enrichment, there's a higher neutron flux and a higher gamma ray signal. So that is an attractive indicator. The disadvantage there is that these plants basically run at near vacuum conditions, so that even though you've got higher enrichments, there still is not much material there, which means trying to measure something with portable, non-destructive assay equipment, it may take a long time. So there still is a challenge there. And referring to earlier, I've primarily talked about 235 and 238, but natural uranium also contains a very small amount of U-234, and should reprocessed uranium be re-enriched, you may have small quantities of 232 and 236. As part of the enrichment process, since it is based on this mass difference between the isotopes, other isotopes will enrich at a different rate than the 235. So looking at this ratio of minor isotopes also is another potential indicator of misuse of the facility. So here's another picture on the upper right is an overhead view showing a cascade where you see centrifuges, hundreds of those in those pictures, and you see a lot of this piping that is used to connect all of these centrifuges together to deliver the UF6 throughout the cascade. The safeguards approach that was developed for gas centrifuge plants were actually developed by the technology holders at that time in cooperation with the IAEA. And they developed what was called an LFUA inspection, a limited frequency unannounced access. This was developed in what was called the hexapartite safeguards project that took place between 1980 and 1982. The technology holders agreed to provide the IAEA with 4 particular activities that could be conducted inside the cascade. These include visual observation, radiation monitoring and NDA measurements, sampling, and the application and verification of seals. So, based on what you've already learned thus far in this lecture, for visual observation, what do you think inspectors would be looking for? They're going to be looking for some of this portable and withdrawal equipment, seeing if by some manner that maybe the cascade arrangement has been changed, maybe get a feel for the number of total cascades, anything to kind of get a feel for how much separative capacity has been installed, how's it being used, are operations and activities being performed as declared. Secondly, radiation monitoring NDA measurements. What are the inspectors trying to do there? They're looking at this U-235 gamma rays and neutrons to see if the enrichment levels may be higher than that is declared. The picture on the bottom shows a high purity germanium detector placed on a 5-inch diameter process pipe in which the UF6 flows through. So you can see some of the challenges associated with, quote, portable, close quote, equipment, that because this material is at such small quantities that some of this equipment has to be large, the fact that the IAEA is restrained from unduly impacting operations means that there's limitations. You're not cutting in the pipes. It's difficult to install things in line. Everything has to minimize impact on operations. So some of the equipment can get quite sophisticated. By sampling, here was the thought that the agency would ultimately retain the right to withdraw a UF6 sample directly from the Cascade. This was never envisioned to be a routine activity, but one that would be the ultimate resolution of a discrepancy if all the other instruments were coming up with a questionable solution that couldn't be resolved. And then applying and verifying seals within the Cascade. What did we say the purpose of containment surveillance was? To provide continuity of knowledge in between inspections. What are some potential applications? Well, we already said earlier that during startup or during emergencies, the operator may need to use some of this portable feed and withdrawal equipment. So generally these cascades may be designed with some of these emergency evacuation ports or whatever else that may only be used one time during their career or during the lifetime of the facility. So it may be possible after the cascade comes online, if these connections could be sealed up in a way, because they could potentially be used for a misuse scenario, but if they could be sealed closed, then the agency could come, as long as the integrity of those seals have been maintained, then they would have confidence that those pieces of equipment had not been used during inspections. So those were the 4 initial activities agreed upon in the 80s. Since then, there's been a couple of other activities developed. One is in the mid-90s, the implementation of environmental sampling, where the IAEA will take cotton swabs, as shown in the top picture, from various places where they had access. And then these samples could be brought back, sent to a very small number of very high-performance laboratories in their network around the world to do ultra-trace analysis that can look at individual particles to determine if there are higher than declared enrichments. Also recognizing the need for some type of continuous monitor as operations had continued to develop. Some technology holders had developed what we refer to as a dynamic, flexible cascade, where you don't necessarily need to do a lot of reconfiguration or valve changes to change the performance. So the picture bottom right shows a sodium iodide detector that could be clamped onto one of the process pipes that could continuously measure this pipe with a very low count rate, but provide kind of a go, no-go answer that there has not been a significant change in the operational level of that pipe. Also, at one facility, they encountered a problem where they were having problems and they had some significant holdup. This was the UF6 that either solidified inside the process piping, either in terms of UF6, or if UF6 interacts with any moisture that leaks in, it will react with the water to form a solid UO2F2 deposit. And so this was a portable neutron detector that was designed to go through to be able to estimate that inventory. So the plants that I showed you earlier were those that are in operation today. Currently, there are a number of new facilities under construction. Now, earlier I mentioned there is already more capacity than demand, right? So why are new facilities being built today? Thank you, Tim. Tim's working on an enrichment profile, so you should know these. Well, there's a couple of factors leading into this. Tim said, and you couldn't hear, the two gas centrifuge plants who combined have a capacity of about 20 million SWUs are being shut down in the near future. So they are the companies building these facilities are racing to replace that. A second factor is there's been a large quantity of the LEU, low-enriched uranium, being introduced to the market from the U.S.-Russia program, where the Russians have been downblending 500 metric tons of HEU back to LEU, and that program is completing its contract in 2013 or 2012. 2013, so there will be the replacement of that. And then thirdly, before Fukushima accident, there was a lot of talk about a growth in the nuclear power capacity around the world. And actually, the early reports, those countries that were pursuing nuclear power, primarily in Southeast Asia, are still continuing with their plans. And so any new power plants will need capacity. So despite this overcapacity that exists, there are several large-scale plants under construction. The first one, the United States Enrichment Corporation, has a license to build a centrifuge plant in Portsmouth. Again, they are using this primarily to replace the capacity of their diffusion plant in Paducah, Kentucky. Urenco, who operates the three plants in UK, Netherlands, and Germany, is building a facility in Eunice, New Mexico, called Urenco USA. Its license is 3 million SWUs per year, with a plan to potentially increase that up to 5,000 or 5,700,000 kilogram SWU per year. Again, this is where they are going after USEC's market here in the United States. Areva is building a centrifuge plant, GB2, the same site as their diffusion plant. This is a 7.5 million kilogram SWU plant to replace their own diffusion plant with a, again, more economical process. And then a new one that's out there, GE Hitachi is pursuing building a plant based on laser enrichment technology. And again, this is looking at a 3 to 6 million kilogram SWU capacity. So a number of new plants are currently under construction. All of these have a target operation, full operation date between 2013 2015. Both GB2 and Urenco USA actually have Cascades online and operation now and are gradually increasing their throughput. So the challenges as these new plants are being built remain the same as they were in the 80s. No means to independently verify separative capacity. The aspects that were classified and proprietary continue to be. The IAEA budget has grown a little bit, but not substantially. And the difficulty of implementing these LFU inspections. When the first plants were being built in the early 80s, they actually only had a capacity of a couple of 100,000 SWUs, and you may be looking at 6 to 8 Cascades. The largest plant that they had envisioned when the technology holders were meeting were on the order of 1 million SWUs per year. Now we're seeing all of these are 3 to 7, or in the case of the one Russian plant, 12 times larger than that. So you can imagine that they may have 60 to 100 Cascades, a much larger footprint, and one of the things about these LFUAs I didn't mention earlier, these were one-day inspections on the order of 1 to 8 hours per inspection with very controlled capabilities. So these larger plants are making it very, very difficult to continue to effectively implement these LFUA inspections. Plus, with all this additional capacity, the time frames necessary for a breakout scenario are much, much shorter. So this is what has led the agency and other concerned member states to look at the tools available for the IAEA and what they could do there. This really started kicking off, and the agency hosted the first meeting of technology holders in Vienna in April 2005 to go back and look at the safeguards approach developed in the early 80s to say, is it still appropriate for meeting the safeguards objectives for enrichment plant, and are there some new tools that should be considered? And without going into the detail, the conclusion was those safeguards measures were still appropriate. However, with the increased size, they were looking at taking better advantage of operator information to see if they could move more towards either some continuous process monitoring by sharing operator instrumentation, also applying what is referred to as SNRI, short notice random inspections, to better address this detectability, the timeliness of inspections. And the agency basically captured all of this in what they referred to as the model safeguards approach, which came out in 2006. It's the technology holders that are, most interested in what the IAEA can and cannot do. I already mentioned they're concerned in that, on one hand, they are obligated to protect classified and proprietary information. On the other hand, there is a strong desire among the technology holders to make sure that the safeguards as applied by the agency is credible, is effective, and is universally applied. One, again, they want, from a commercial advantage, they want everybody to share the same inspection burden. Secondly, they are especially concerned about enrichment plants in Iran, North Korea, and other places, and want to make sure that the agency has the right tools to be able to draw credible, independent conclusions. So the Department of Energy followed up on the IAEA meeting by hosting a meeting. It was actually here in Oak Ridge in 2008 to look at some of these measures that were actually being developed that were identified by this model safeguards approach. And this was a meeting to bring more of the technology holders together to talk about these measures. Representatives from URINCO were so interested and pleased with this conversation of being able to talk directly with the IAEA, other operators and the technology holders that they hosted a second meeting at their facilities, outside their facilities at Capenhurst in the UK the following year in December 2009 to continue this discussion. And currently we're in process now of looking at having another meeting sometime in the spring of 2012. I won't say it here because it hasn't been finalized yet. So look for item M papers on this topic in the future. So the IAEA needs, I mentioned some of these earlier. What was identified at this 2005 meeting was the ability to be able to conduct short notice random inspections at facilities, to be able to have some continuous monitoring of these operations, shared use of operator data, looking at continuously monitoring items of interest, and here particularly these cylinders containing the UF6, and also abilities to be able to analyze some of these samples on site as opposed to shipping nuclear material to laboratories, back to Vienna and to laboratories around the world. So safeguards measures that have been investigated over the last half decade are this measures that would allow for continuous unattended verification of UF6, either tracking of the cylinders as they move around on the plant site, looking at some of this equipment the agency uses, such as process scales where they weigh every cylinder when they're full and empty for the MC&A activities, looking at trying to improve their online enrichment monitoring capabilities to verify that the enrichment has not exceeded the limit for the plant. And also, as I mentioned, the agency, the facility operators do a lot of measurements on their accountancy scales. And so if there is some way that the agency can share information and data directly from these scales, it would cut down on having the operators repeat these measurements in their presence. The other two bullets, again, portable analytical equipment to provide more timely information to the inspectors in the field, and looking at better tools for verifying the design information. One of the requirements of these facilities that are under inspection, they provide a design information questionnaire that describes the facility layout and how they interact with the Cascades. And part of the agency's requirement is to look at these excess LEU and HEU production scenarios as well as diversion scenarios and identify physically what types of changes might be required, and looking at tools for being able to verify that the plant design has not changed. Cylinder tracking, here's just a couple of pictures of some cylinder yards. The bottom right are 30B cylinders used for containing the enriched UF6, so you can see an inside storage with dozens of cylinders present. The other two pictures are two pictures of external cylinder storage areas. Each of these cylinders can contain up to about 14 tons of material. You can say they can be quite large. The picture on the right is a European facility where you can see hundreds of cylinders there. The bottom one is the Paducah plant. So after 50 years of operations, they have acquired 40,000 plus tail cylinders. So as an inspector, if you're trying to verify that the content of none of those have changed, you can see what a daunting task that would be. Mentioned earlier, when not in the process, the UF6 are in these cylinders, and part of the continuous operation that takes place at the plants are to connect these cylinders to the process and either transfer material from the cylinders to the process or from the process to the cylinders. So if there is some way to monitor continuously these feed and withdrawal activities, it could significantly change both the frequency of inspections and the activities the inspectors have to do when they're at the site. Here is just one schematic showing from a verification experiment we did a little over 10 years ago that shows basically a week's worth of data from one scale. This scale was calibrated such that the full weight gave a 0 reading. So you can see over time the weight value drops off as the cylinder is emptied. You see spikes as these cylinders are actually replaced, moved from the scale, put back on the scale. You can also see when an operator steps on the scale, other activities, but you can come up with a profile of operation. So in this one particular period, you can get information that both 2 cylinders was processed on this scale, and by looking at the difference, you can get a rough approximation of how much material was transferred from these cylinders to then compare with the actual facility declarations. DIV instruments, actually the Joint Research Center, a subset of the European Safeguards community, has developed a 3-dimensional rangefinder that you can set up and take a couple of a minute measurement and take a 3D image of the location, and then at some time later you could come back and take a second image and immediately look to see any differences that may have taken place. We're also, since we're interested in actually the material flowing through and not just the design, we are actively working right now on combining this laser rangefinder with some gamma or neutron imaging equipment that could either also show the change of flow through pipes that have not physically changed, or if the material itself flowing through pipes has a different characteristic. So a lot of interesting R&D taking place. While we are focusing on these large facilities right now to try to minimize an increase in the amount of effort the agency has to apply to them as they grow larger, we're also mindful of the application to smaller facilities as well to make sure that the same technologies are indeed appropriate. So to close out, I guess a few final thoughts. This new construction and enrichment facilities and the expansion of capacity in some of the existing ones has reinvigorated within the safeguards community the discussion of looking at the efficiency and effectiveness of the IAEA safeguards measures for the first time since the early 80s. And this has really been taking place over really the last 7 or 8 years. In response to this, the agency has developed a new model safeguards approach that has increased some of the tools at its disposal for reaching the safeguards objectives at specific facilities, and this has identified some additional tools and techniques that are yet to be demonstrated. A number of member states, including the United States, is actively doing R&D at some of these measures to see if we can prove the capability to improve the verification activity, and we are looking at the universal application of these measures once they become accepted as approved IAEA measures. So thank you for your time and attention. Any questions from this distinguished audience? Yes, sir.
Have any of the weapons states invited the IAEA to carry out safeguards and enrichment plants, and if so, why is that a priority for
Very good question. Two-part questions. Has any of the nuclear weapon states invited the IAEA to carry out safeguards at their facility? And the second one, why would that be a priority for the IAEA to implement safeguards in weapon states, right? So the answer to the first, yes. Capenhurst plant, one of the 3 Urenco facilities, is in a weapon state, the UK, and that has been one of the requirements as a member of Urenco, that all Urenco facilities have equivalent safeguards. Within the United States, what we did see was during an earlier downblending activity where the United States wanted the IAEA to verify to the rest of the world that material that we had declared excess from our weapons stock was indeed downblended to LEU. There was at that time a verification experiment that took place at the Portsmouth Gas Centrifuge plant where the agency verified it was about 5 metric tons of HEU was indeed blended down. Currently, within the United States, as part of our list of facilities eligible for IAEA inspection, the diffusion plant, the centrifuge lead Cascade are all on the list, as well as the Urenco USA. So the agency is free to select those. The question as to why the IAEA would want to is one with a number of valid arguments. On A, they've got a very limited budget, so why would they want to send inspectors to weapon states as opposed to focusing their effort to non-weapon states? And there's a couple of reasons for that. One, there's the equal burden principle that it would not, you wouldn't want facilities in weapon states to have an economic advantage because they don't have to bear the same cost of hosting inspections. Secondly, weapon states can provide maybe even more openness and transparency that establish the IAEA the capability for implementing a current tool which can then become the standard for other facilities. From the, my experience in supporting the Department of Energy in hosting inspections on just a storage vault, we were able to learn a significant amount just from interacting with the inspectors to learn ways to better help them do their job in the field that would help them more effectively implement their inspections across the board. Thank you.